Hi everyone, I am Momin Abbas along with my teammates Mohabbat, Huzaifa Arif, Tobias Park, and Yingyang Sun. Today we will present our project Online Learning Grade Adaptation with Hypergradient Descent. The overall holistic idea of our project is to adaptively tune the learning rate, also known as a step size, with the aim of achieving faster convergence on various machine learning optimizers. The outline we will follow is as shown. First, we will build the motivation of our project by explaining the problem statement. Then we will present the solution along with the algorithms. We will show our simulation results before finally moving towards the convergence analysis. Giving a brief background of the literature, the idea of tuning hyperparameters is not old. In fact, finding good hyperparameters is itself an optimization problem, which can be solved using another level of gradient descent. For example, using bilevel optimization to optimize hyperparameters is recently a very popular research topic. However, solving such nested optimization problem is very tedious and computationally very expensive. Furthermore, per parameter-based adaptive learning rate used by optimizers like ADAGRAD and RMS-prop require initial learning rate, which also needs tuning. So the problem is that conventionally, the way learning rate is tuned is very manual method, which is not only tedious, but also expensive. For example, most of us use either line search or grid search like methods. Furthermore, talking about adaptive learning rate tuning, here we would like to emphasize that optimizers like RMS-prop and ADAGRAD do actually update the learning rate dynamically. However, these algorithms are initialized with a fixed global learning rate that still needs tuning. So the question is, what's the solution? Well, in order to find the optimal learning rate with lesser manual tuning, we propose adaptively tuning the learning rate using only first-order information. The idea was originally proposed in this paper by Bedin to achieve better convergence for various gradient-based optimizers. The details of the paper are as shown. It was published in the 2018 ICLR conference. In our project, we demonstrate the effectiveness of the proposed method, termed as the hypergradient descent, on various optimizers, including stochastic gradient descent with Nesterov and Adam, and on various datasets and various architectures. Using our results, we derive some useful insights on the improvements as well as the limitations of the hypergradient-based method.
So what is hypergradient descent and how exactly does it work? So first, let's start off just by thinking about normal gradient descent. As we know, normal gradient descent is defined by this equation here. Theta t equals theta t minus 1 minus alpha times the gradient of f at theta t minus 1, where theta is the parameters, alpha is the learning rate, and f is the objective function. So let's call this gradient descent equation 1 for now. So we're going to add on to this gradient descent formula a little. So we have an update rule for the parameters using gradient descent. But in addition to this, we also want to have an update rule for the learning rate alpha itself. And the way we're going to incorporate that is by looking at the partial derivative of the objective function f at t minus 1 with respect to the learning rate alpha. So if you look at the equation in the middle of this slide on the left, that's that over there. Now we're going to take that and expand it into the thing on the right. And you notice that these two things are basically equivalent. So on the right here in the numerator, where you see theta t minus 2 minus alpha times gradient of f at theta t minus 2, by the gradient descent formula, equation 1, this is just theta t minus 1. We're literally just substituting in equation 1 for gradient descent here. So these two things on the middle are equivalent. So when we simplify that a little, we get this here on the bottom. And if we apply the chain rule to that, you'll see that this is just the thing on the very right here on the bottom. And we're going to call that equation 2. So as you can see from the slide, interestingly, it works out that the partial derivative of the learning rate is really just the multiplication of our gradients from our original problem. And that'll be very important later on. So putting all this together, this allows us to create an update rule for alpha. So basically, we're going to apply gradient descent on the learning rate alpha itself, as you can see at the top here. And then if we substitute in equation 2 from the last slide into this new gradient descent rule for alpha, we get this, equation 3, which is basically the idea behind hypergradient descent. You'll notice we did introduce an extra hyperparameter beta now, which is basically the hypergradient learning rate, or like the learning rate for the learning rate. We'll see a little later in the presentation, we don't actually need to worry about the value of beta too much. So then now our parameter update rule for our model is the same as before, just gradient descent, except now at each iteration, we use the updated learning rate alpha t for that iteration. And that's basically the idea behind the algorithm. And you'll notice this doesn't really increase our cost or decrease our performance much at all. In terms of memory, all we need to do is store one extra variable, just the product of the gradients, to calculate the partial derivative of the learning rate. And in terms of computation, all we've introduced is one additional dot product. So just to make it super clear, this slide shows the difference between SGD and SGD-HD, or SGD with hypergradient descent, side by side. So in SGD, we compute our gradient, call it g of t, we multiply it by the learning rate, and we subtract those to get the new parameters. In SGD-HD, we still compute our gradient g of t, but we also compute this new variable h of t, which is just the product of the gradients we talked about. And then this delta alpha u t minus 1 term you see here is also a variable that has a product of just our previous gradients. So we're multiplying those to get our new product of gradients h of t, and then we compute our updated alpha, and we use that to finish the normal gradient descent algorithm. So exact same thing here. This is just showing the same thing with SGDN, SGD with Nesterov. So it's the same thing. We're just maintaining the product of gradients to compute an updated alpha at each iteration, and that's the only difference here. And then exact same thing here, just with Adam. Again, we're just keeping track of the products of the gradients to compute a new learning rate. Everything else is exactly the same.
Okay, for fair comparison of standard optimizers with their improved hypergradient descent versions, we evaluate the 6 optimizers: stochastic gradient descent, SGD with Nesterov, and Adam and their hypergradient descent versions. On the we applied them on 5 convex and non-convex models and 3 datasets: MNIST, CIFAR10, and CIFAR100. MNIST and CIFAR10 are 10 classification datasets containing 50,000 training and 10,000 testing images. And CIFAR10 has 100 classes, making it more difficult. So let's look at the result of hypergradient descent on logistic regression. This is a very simple machine learning model out there, and with a very simple dataset, MNIST. There are 6 optimizers we have: SGD with Nesterov and Adam, and with their hypergradient versions. And we can see right there, the purple, the blue, and the green lines are Adam, SGD, and then SGDN. While the overlap lines we find way down below, the ones that are almost immediately converged, are versions with hypergradient descent, with the Adam HD converges the fastest over the 100 epochs we're training. The same trend follows for test accuracy, with the ones with hypergradient descent converging at the fastest and reaching their accuracy, while the vanilla ones will not reach full convergence within 100 epochs. Now, here are the results of the same optimizers on the same dataset, but with a different model, multi-layer perceptron. In this case, the same trend holds. The SGD, SGD, and Adam are having worse convergence than their counterparts with hypergradient descent. We can see that the difference does not seem to be as drastic as we saw in the previous slide, where we used the logistic regression. The accuracies of hypergradient descent version all have a greater accuracy. Still a good increase that makes it worth the effort to implement hypergradient descent, though. What would happen if we use a more complex dataset, the CIFAR10, with colorized images making the classification model more complex? Will optimizers with hypergradient descent hold the edge over vanilla optimizers? The answer is yes. The blue and green lines are SGD and SGDN, which as we would expect, are slower than the hypergradient descent versions. The brown line showing the Adam HD hypergradient optimizer is also having drastically better convergence than Adam. But now we see the purple line here. Adam is better than the cluster of SGD HD and SGDN HD. This shows hypergradient has a performance boost on the optimizers, but seems though that the more complex model, as more complex the model and data set get, the less effective hypergradient descent becomes. To find out if this is the case, we need to dive deeper into the problem. Now, Robot is going to talk about the performance of hypergradient descent on convolutional.
Hi, this is Mobile. So far, we have talked about all successful cases and simpler models. Let's explore more and find out the limitations of hypergradient descent-based optimization on more complex datasets and models. Though the paper does not evaluate HD on most popular models except VGG, we evaluated HD on ResNet and wide ResNet to identify its limitations. ResNet is a well-known deep classification model. When we trained ResNet on CFAR10, the loss for all HD variant was lower than their original classical variants. The difference in accuracy on the right side is noticeable. All HD variants achieve higher accuracy in fewer epochs and also achieve higher accuracy after 100 epochs. We could also see similar convergence graphs when we trained ResNet 18 on C400, despite the complexity of learning 100 classes. ADAM HD outperformed the rest of the optimizers. As we increase the model complexity to ResNet 101, we can see the difference in loss by using conventional optimizers and HD variants decreases. However, the HD-based optimizers show better performance, which can be observed from the right side plot of accuracies. When ResNet 101 was trained on C400, we could observe in the left plot that the loss for HD variant optimizer is better than the simpler variant. Also, in the right side plot, accuracy for HD variant is higher. Wide ResNet is one of the popular 52-layer deep classification model built upon ResNet. When we trained it on C400, the model shows a better performance for all HD optimizers. In general, HD optimizers can improve the performance for any model regardless of the model complexity in the dataset. However, the more complex model would require a better training or better value of the beta.
So let's talk about the observations we had while running these experiments. We observe how the learning rate behaves with time. For the sake of simplicity, we show the learning rate behavior with time for ResNet 18 on CFAR10 and CFAR 100. We can see an initial growth followed by a fluctuation around a small value of the learning rate. We also observe from our previous results that convex objectives have a marked improvement on accuracy, but for complex data sets on non-convex objectives, we do not have a consistent marked improvement. For a set of beta parameters we tested, we always have relatively faster convergence irrespective of the choice of our initial learning rate. The figure shows the performance analysis for a pair of initial learning rate and beta parameter. This analysis is done between vanilla SGD and SGD with hypergradient descent. The values in the grid are the number of iterations, after which training loss was 0.29 for logistic regression on MNIST. We can observe the clear benefit of using hypergradient descent, at least in the convex setting. The number of iteration required are much manageable regardless of the choice of initial learning rate and beta. Another benefit is that we see a marked improvement on adaptive algorithms like ADAM. A benefit that was observed was that for ranges of alpha naught that seemed to converge quicker and had better test accuracy, using hypergradient descent even improves the performance compared to those supposed optimal initial learning rates. Beta fine-tunes in finding optimal learning rate. The behavior of learning rate with iterations motivates an extension of the hypergradient descent method, and we provide a convergence analysis for that extension. The paper makes an argument based on the empirical behavior of alpha t, that we smoothly transition to a fixed learning rate as t approaches infinity. Concretely, the step size we choose to update our parameters is defined as follows. We call it gamma of t. The modified adaptive step size gamma of t is defined as delta t times alpha t plus 1 minus delta t times alpha infinity, where we choose alpha infinity to a fixed value to be strictly less than 1 over L, where L is the Lipschitz smoothness constant. Delta t is chosen so that delta t times t approaches 0 as t approaches infinity. If the function is f convex and L Lipschitz smooth, such that the norm of the gradients are upper bounded by m, then applying the triangle inequality and the Cauchy-Schwarz inequality on the alpha update equation, we have the upper bound on alpha t as shown by equation 4. This upper bound is a linear bound in time, since we know that a linear term times delta t approaches 0 when time goes to infinity. Therefore, the modified adaptive learning rate, gamma of t, approaches alpha infinity as t approaches infinity. Therefore, for large enough t, we have gamma of t upper bounded by 1 over L. Hence, if we choose alpha infinity to be upper bounded by 1 by L, for this constant step size and the assumptions on f held above as true, we have already shown convergence of gradient descent. You can refer to lecture notes for detail on this particular claim. We thank you for our presentation, and the floor is open for questions. Thank you.